Alright, in this video, I'm going to go over graphing derivatives again. So in the previous video, I showed you how you can graph a derivative by using a table. So what you have to do is, pick a bunch of x values and estimate the slope at those points. Now, there's a little more efficient way to do that. It's not quite as accurate because you're not going to get as many points. But instead of doing a table and graphing a whole bunch of x values, just pick the ones that are important. So to think about which ones are important is which points have a slope of 0. So the first thing is find x values where f prime at x equals 0. So where does f prime at x equal 0? Well, that's when the tangent is horizontal. So that would be around here. So there we have a horizontal tangent, and around here. So that means that the y value of the derivative is going to be 0 at these points. So we're going to have x-intercepts at these points. So I'll put these points on my graph. So I have an x-intercept of 0, x-intercept of 0, or the y value 0. So that's for my derivative, because these have horizontal tangent. Another important point you're going to look for is if the derivative is ever undefined, so if you had a corner, cusp, anything like that, horizontal tangent, that would be important too. So x values where f prime at x doesn't exist, but that doesn't happen in this giving the graph that I have here, but it might happen in other ones. If it's a polynomial, like it's a cubic looking polynomial or a cubic looking graph, you wouldn't have any points where f prime doesn't exist, but could happen for other types of functions. So another one would be try to find the points, and this is going to be an estimate. So estimate where f prime at x would be, where the slope of the tangent would be the biggest and smallest. So estimate where f prime at x, so that's the slope of the tangent, is biggest slash smallest. So for this one, I'm going to look, I'll look between these two x-intercepts. So on this part where it's decreasing, so I know that it's decreasing. So when it's decreasing, that means that the tangent has negative slope. So where is the tangent kind of the steepest? So it'd be kind of somewhere right in the middle, right? Right around here, if I were to draw the tangent, that's going to be like about, I don't know, that steep. And that's going to be steeper than, say, over here, right? It's less steep there. It gets steeper and steeper as you go down here. So I'm going to try to estimate what this is, just the same way you did before when you did it using a table, but I'm just doing this point. So this one I'm going to estimate, I don't know, it's negative, if we do the rise over run triangle, maybe about -2. So I'm guessing that the slope of the tangent for this one is -2. So -2 is down here. So it'd be around here. So that's when it's the smallest, right? It's the biggest negative number. Now for the biggest, there actually won't be a biggest, because let's say this portion of the graph over here, well, the tangent's positive, but it's getting more and more positive. Like it's getting steeper and steeper as you go. So that means that the slope of the tangent is getting bigger and bigger. And the same thing on this side, it's getting more and more positive as you go down. So there wouldn't be a biggest or smallest on that interval. So I've got these 3 points, two x-intercepts, which corresponded to the tangent being horizontal, and this point here, which I estimated to be my steepest. So this is going to sort of be my minimum point because it has the largest negative slope. And then the fourth step is basically connect the dots. So I have those 3 points, so connect the dots. So it also helps to take into account, okay, it's a cubic, so I know that the derivative should be a quadratic. So I'm going to connect these dots, but then make it look quadratic. So thinking about things like that helps. So this red one here is f prime at x. Should have labeled the black one, but the black one was f at x. So it's kind of similar to what we did before where we did a table of values, but here I'm not going to do all the x values or a whole bunch of x values. I'm just going to take the ones that are important, and that will allow me to get the general shape of the graph. Okay. Okay, here's the second example. So here I've got a function f. It looks a little bit different. It's a combination of different types of functions. I'll put a scale there. Let's say that's 1 and that's 1. So the same steps when I go to do this. So first thing, decide where the function is f prime at x equals 0. So that would be wherever the tangent's horizontal. So that would be right there. So there, that means I have an x-intercept for my function, for my derivative. So my derivative is going to intersect the x-axis there. The second step is to decide where f prime at x does not exist. So where it doesn't exist is at these two corners right here, right? So that means that these points are not going to be in my domain for the derivative. What's happening at those points? Well, there could be different things. It could be a hole. It could be an asymptote. If I look close to, as I'm going at this point, this corner or cusp from the left side, notice that it kind of looks like a circle, so or a semicircle. It basically is becoming vertical. So if it's becoming vertical, that means you're gonna have that means the slope of the tangent is approaching infinity or negative infinity, right? It's getting to be a vertical tangent. So that means you're going to have a asymptote. If the slope of the tangent is approaching infinity, so approaching a vertical line, then you've got a vertical asymptote. And the same thing happens over here, but only on the one side. Now notice this portion here, this is a straight line, as is this portion. If you have a straight line, the tangent or the slope of the tangent is easy to determine because it's just the slope of the line. So in this case, I'm going to estimate the slope of the line. So let's see, that's 1. 1 there, and then 2 would be up there. So the rise is about 1 over 2. So here I'm going to estimate the slope of the tangent at every point along here to be equal to a half. So it's a constant of a half. An open circle here because you're not going to include that in the domain because the derivative does not exist at that point. Same thing for this one. I'm going to have to calculate the slope. So here it's a negative slope. This one looks maybe more like it's negative 1. So negative 1's down there. So just by doing the rise over run. So I've got there. And now in between these 2 points, this is my x-intercept, and I've said over here the slope is going to be negative, but it looks like it's approaching negative infinity. So it's going to be going down to negative infinity, approaching that asymptote. And then for this portion, it looks like it's approaching positive infinity. So it's going to be going up like that. So it's going to look something like this. So that'd be f